Hi everyone, this is Kalyan Kumar and welcome once again to another episode of Gaseous State in Chemistry Tutorials. We have been doing gaseous state for quite some time now. We have done 7 episodes. This is episode number 8 and this is titled the Maxwell-Boltzmann Distribution. If you've missed any of those parts before, then I suggest you go through those parts and then come to this video. And I'll be putting the link of all those videos in the description below. So let's get on with the video without wasting any more time. So we are looking at the Maxwell-Boltzmann distribution, and there is a bit of an introduction that is required to understand this. Now I'm going to show you a picture. This is the picture of James Clerk Maxwell. And this person and his wife Catherine Maxwell and their pet, James Clerk Maxwell, worked in electromagnetic induction along with Michael Faraday. Of course, they never collaborated, but he worked with Michael Faraday for quite some time, and he was interested in electromagnetism, also worked in electromagnetic induction, and due to which he was able to give the electromagnetic theory of light. He was able to explain for the first time how come light, being a wave, is able to travel through the vacuum in space, because it was assumed that any wave would need a medium to travel. But light doesn't, and he was able to explain that by saying that light is basically a stream of energy due to the fluctuating electric and magnetic fields perpendicular to each other. And that was able to explain many properties of light. One, that it's a wave, and secondly, the fact that he was able to explain that it is moving without a medium. The next picture you will see is the picture of Ludwig Boltzmann. Now, in fact, James Clerk Maxwell is less known for his theory on color photography. In fact, he pioneered in the fact that he was able to discover that white light is made up of red, green and blue. In fact, he's the one who proposed the RGB theory of light. Ludwig Boltzmann is regarded as one of the founding fathers of statistical mechanics, where you use the concept of probability to explain the macro nature of any system. And what did they do? They did not collaborate together. They worked independently and they arrived at the same conclusion. They were talking about speed of air molecules. In fact, this was done by Maxwell. Boltzmann was able to generalize this theory to include more and more number of gases. So speed of air molecules is what they were studying. And the entire theory of theirs is based on statistics and the probability theory. Now here I'd like to give you an idea about probability, in the sense that we may sometimes wonder, why are we giving that much importance to probability? Because probability is never going to tell you what an actual event is going to look like. For example, one might say that if I toss a coin, I got 50% chance of getting a head and 50% chance of getting a tail, but I get only one of them. So what's the big deal about this probability? Well, probability never works for an event that occurs once, twice. It is meant for a very, very large number of events, number one. Or maybe a system containing large number of particles like molecules, atoms and stuff like that. And you know that gas molecules, even if they're just 1 mole and 1 mole, you can imagine how big is the number of atoms or molecules in it. So probability works for macro systems. Now, again, coming back to this tossing of a coin, once if you toss a coin, you may get a head or a tail. Assuming, of course, the coin does not have any bias and it is equal probability of getting both. But the fact of the matter is, what happens when you toss the coin 1 million times, 10 lakh times? The chance, of course, the probability says you get 500,000 chance of getting a head or 5 lakh heads. You may not get 5 lakh heads, but you'll get something very close to that. You increase the number of tosses. You do it 2 million times, 20 lakh times. The chance of getting head becomes even closer to 50%. You do it 3 lakh times, you do 30 lakh times, you do 40 lakh times. You keep increasing the number of attempts, the number of events, and you will find that slowly and slowly there comes a time when probability almost meets the truth. So if probability says this is the number of heads you're going to get, you'll get very, very close to that when the number of working experiments, the number of attempts is increased, or the size of the system itself is huge. Alright, so what did they do? They talked about the speed of air molecules, as I said. So let's do a thought experiment. Let's say we have a container, and for the sake of simplicity, I'm going to take nitrogen molecule instead of air, because air contains both nitrogen and oxygen. So I'm going to take nitrogen molecules, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 molecules in it. Obviously that is not possible, but anyway, let me do it. I got another container also containing 10 molecules, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this also contains nitrogen. The difference is, the first container is at 300 K, temperature is 300 Kelvin. The second container, let's say, is at temperature 200 Kelvin. Now what does this temperature mean for the gas molecule? Well, for us, the temperature could mean that, it's very hot, it's very cold. But for a gas molecule, the temperature manifests itself in the form of kinetic energy. So a high energy system will have higher kinetic energy, a low energy system has lower kinetic energy. And we've already seen in the case of kinetic theory of gases that the kinetic theory of a molecule, of one molecule, is 3/2 kT. And this is, remember, the average kinetic energy. You cannot determine the kinetic energy of a molecule, you can only talk about the average value. So 3/2 kT, so it's directly proportional to temperature. So this means the molecules at 300 Kelvin have greater average kinetic energy than compared to the molecules at 200 Kelvin. Now remember, they have various speeds. Each molecule has different speed and as well as different direction, therefore different velocity. They're all moving in different directions. Same here. It is even possible that there may be a molecule in the 200 Kelvin system which has a speed greater than any of the molecules at 300 Kelvin. That's possible. Because remember, a single molecule can have almost anything that you can think of. But the fact is, the average value of kinetic energy of 300 Kelvin is greater than 200 Kelvin. So they were trying to figure out the speed of air molecules, because kinetic energy, as you know, is half mv squared. So they were talking about, okay, let's try and figure out what could be the velocity. So they had a way of doing it. And the way they did it, they used some theoretical models and some high level of mathematics and physics, and they were able to come up with a graph like this. And both of them were able to do it independently. This axis represents, the x-axis represents the speed, and the y-axis represents the number of molecules. So y is representing number of molecules, x is representing speed. Remember, it's not velocity, it's speed. And here again, you need to understand the difference between speed and velocity. Of course, I'm sure you do understand what that is. Velocity is a vector, speed is a scalar. But I am drawing a graph. In fact, the graph that these people came to was based only on speed, not on velocity, because they were very clever. They knew that if they had to go with velocity, velocity can take negative values also. Which means whatever graph they draw on the positive x, they would have to draw on the negative x as well. So they were only interested in the scalar part of it, the value of the movement, and that was speed. So we will draw the graph only the positive x, because we are only using the graph of speed versus number of molecules. Now here, different molecules will have different speeds, and the graph goes somewhat like this. So let's assume this is the graph of the 300 Kelvin one. Let's say this is 300 Kelvin. So what do you notice in the graph? The graph starts at 0, both are 0. The speed is 0 and the number of molecules is 0. And as you find more and more molecules, you get more and more speed until you reach this point. At this point, you get some particular speed, but this speed is unique because this is the speed that maximum number of molecules have. So let's assume, again, take a theoretical system, 10,000 molecules there. And assume that this value, the maximum number of molecules possess 2000, let's say this is 2000. Now you may wonder, why not more than 5000? Shouldn't that be more than 5000? No, because remember, if this is 2000 here, there is not a single velocity. Let's say, for example, this velocity is not possessed by molecules which are 2000 or more. It is possessed by less number of molecules. So maximum number of molecules possess this velocity of 2000, but that doesn't mean it is the majority. In fact, if you look at the next point, the point very close to this 2000, let's say that is how much? 1999, then you have 1998, then you have 1997, because it's a smooth graph, all points are there in the graph. So if you were to add all that up, you will automatically realize that that will be greater than 2000 if you add all these molecules. You add all these molecules, you will find that that value is greater than 2000. So remember, though this speed is possessed by maximum number of molecules, that doesn't mean it is possessed by majority of molecules. Just like in a country, in a democratic country, you have an election, let's say there are 8 parties contesting the election. One party get 30% of the votes, each of the 7 get 10% each. But since none of the party got more than 30%, so the party which got 30% vote forms the government. But remember, 70% voters didn't vote for that. So it's not a question of majority, it is a question of maximum number. So if 2000 have one particular velocity and no particular velocity can be had by a group of more than 2000 particles, then that is the maxima. Okay, so this is how this graph is going to look like. Now let's say, what would happen if I were to have a 200 Kelvin? Now what you need to also understand is the broadness of this graph. Can you see it starts here, speed, and goes up to here? So it is said that greater this temperature, not only is more the kinetic energy because of this equation, it is also true that broader the graph would be. That means the range of speeds would be higher. So you start from here and you go here. As you go on decreasing temperature, let's say 200 Kelvin, 150 Kelvin, 100 Kelvin, and so on, this graph becomes narrower and narrower and narrower. As a result, the peak would go up. So if let me just remove all of this. If I were to draw the graph of the same nitrogen molecules at 200 Kelvin, it would probably look like this. As you can see, the range is decreased because the temperature is decreased, so the range of speeds have decreased. The maximum speed, which is this, is lower than the maximum speed which can be there at higher temperature. So that's absolutely fine. But since it has become narrower and the area under each graph represents the number of molecules, and I took the same number of molecules in 300 and 200 Kelvin, you'll automatically find that this has to peak up. So the peak of the blue curve, the lower temperature, would be higher than the peak of the red one. But remember, the speed that maximum number of molecules possess, this U1, and if this is U2, obviously U2 is lower. Lower temperature will have lower velocities. But remember, if 2000 molecules possess this, then this is possessed by, let's say, 3000 molecules. Which means as you lower the temperature, the number of molecules having this particular speed, the speed which maximum molecules possess, that number increases in that particular group. And which is why it is becoming narrower. So it becomes narrower and higher in height. What would happen if I were to take a system which is 400 Kelvin? Well, it would look somewhat like this. As you can you see the green graph has a greater range of speeds than the red one? But can you see the peak has decreased, But obviously this value of this velocity, the value of this velocity is definitely greater, but the number of molecules which possess that has fallen down. Even though that is still the maximum for the green, any particular velocity possessed by maximum number of molecules is still the maximum value. I mean, this value is obviously lower. So now let's say only 1000 molecules possess this particular speed, and this particular speed is actually called the most probable speed. So this is what this entire story is about, the Maxwell-Boltzmann distribution. So let's go ahead and have a look at the Maxwell-Boltzmann distribution. We're going to make some assumptions. These assumptions are very similar to the assumptions that was made in the kinetic theory. In fact, Boltzmann was one of the persons who helped develop the kinetic theory. So obviously he's bound to use the same assumptions in getting his theory. A gas is a collection of point masses separated from one another by large empty spaces and moving randomly in all directions. This is not difficult to understand. During the motion, they frequently collide with one another and with the wall of the container, which is what causes the pressure. The pressure is because the molecules collide with the walls of the container. Due to this, speeds and velocities of individual gas particles are not same. That is not to say that all gas particles have different speeds. There are several groups of gas particles with each group having different speeds. Makes a lot of sense. So it's not that if you have the lowest velocity as 0 and the highest velocity as let's say 500 meter per second, it doesn't mean that, you know, in this particular range, every molecule is having different speeds. There are groups of molecules. So one group has U1, one group has U2, another group has U3, and so on and so forth. So there are various groups of these molecules possessing a particular type of speed. The number of particles in a group may vary. That, of course, is seen in the graph. It will not be possible to determine the speed of any random particle. But using probability considerations, it has been made possible to work out the probabilities of a particle to exist in a different speed interval. So using probability, using this graph, one can say, okay, what are the chances that, you know, this particular molecule could be in this category or that category? And that is why we talked about the most probable speed. This distribution is referred to as the Maxwell-Boltzmann distribution. And although the speed of individual particles will vary during collisions, the number of particles existing in a given speed range remains constant at a given temperature. Yeah, because if a molecule, let's say, has 500 meters per second, another is moving at 200 meters per second, they collide, collision is elastic, no energy is wasted. So this transfers its momentum here, may not be complete. It will transfer some energy to the other molecule. So the 500 may become 200 and the 200 may become 500. The idea being that the number of molecules in a given range more or less remain constant at a given temperature. So based on this, they developed an equation. In fact, the graph was the graph based on this particular equation. The equation looks pretty complicated. We're not going to go into how it was derived. It's a very complicated mathematical and physical model, and therefore we're not going to go to derive this, we're going to only understand it. So what do each of these parameters mean? Dn is the number of molecules. Dn is the number of molecules that exists between the time interval of u, of the speed interval of u and u plus du. So Dn, number of molecules having speeds between u and u plus du. N is the total number of particles at that moment. M is the molar mass. U is known as the root mean square velocity. I'll come to that. I'll come to first of all, what do you mean by root mean square speed or velocity, and why are we now substituting speed with velocity? Because u here represents actually the speed. But for this root mean square speed, the speed and the velocity are basically the same. So, and du is the velocity interval. So if I bring the n down, this guy down, I get the fraction of molecules. And then the fraction of molecules having speeds between u and u plus du. And if I bring the du also down, I get the fraction of molecules of speeds u and u plus du per unit interval of speed. So for every interval of speed, the fraction of molecules having speeds between u and u plus du is 1 by du dn by n. And it is this graph that was drawn that I had shown in the beginning. So what you need to understand is it doesn't really matter what is in the y-axis as long as it is proportional to the number of molecules. It could be number of molecules themselves, it could be fraction of molecules, it could be percentage of molecules, it could be number of molecules per unit interval of speed. It doesn't really matter as long as it is proportional to the number of molecules. So let's understand some of the properties of this graph. Some of them we have already discussed, some of them we're going to discuss now. What's the area between U1 and U2? What this means is I had drawn this graph between this and speed. I got a graph like this. So if I take U1 on the x-axis and U2 again on the x-axis, what does this area mean? Can you guess? Now, if you look at the integral, it should go something like this, right? This is the integral of this, and du will get cancelled. So what do you get? You get this. So what does it mean? It tells you the number or the fraction of molecules, because the y-axis is fraction. The fraction of molecules having speeds between U1 and U2. So area under the curve represents the fraction of molecules having these speeds in between U1 and U2. The second is, again, we talked about this already. The curtain opens and you get the most probable speed. So what does this indicate? Well, as I said, this is the speed possessed by maximum number of molecules, and it is this fellow. This is the speed. This is UMPS, most probable speed. And now if you remember the equation, which I'm sure you don't, now you don't have to learn this equation, by the way, at least not in this stage. Not when you're in grade 11 or 12, you don't have to remember the graph. 2 pi RT. This was the original equation. I remember the original equation. And u square upon RT, I guess, u square du. And I'm going to cut off the du because du and n have come on the left side. So I remove them. And this is n and this is 1 by du. This is the y-axis. Now this was the equation, right? Now initially, as you can notice, the curve increases because here u square is dominant. Initially u square is dominant and u square is the one which is pulling the graph up as the x-axis increases. But remember, the effect of u square is diminishing while the effect of e to the power minus mu square, being an exponential function, this increases more rapidly, and this increases less rapidly, and therefore its effect will be less over a period of time. So you find that the slope is decreasing, and which is why after some time it goes down because this becomes dominant now, e to the power negative mu square by RT. So initially, the u square factor increases, which is why the curve goes up. Therefore, the curve is parabolic near the origin. And as the u increases, the factor of e to the power negative mu square by RT starts dominating. So the rate of increase decreases, which is why the curve is more getting flattened towards the x-axis, and then the function starts decreasing. And whenever function increases first and then decreases, you are definitely going to get a maxima. And it is this maxima which is the UMPS. And so the speed where the graph passes to the maxima is the most probable speed. The most probable speed is the speed possessed by the maximum fraction of molecules. This does not mean majority, we discussed that. And the group of molecules that possess this velocity contain maximum number of particles. Now, just to boggle your mind a little bit more, I remember I took the example of nitrogen. If you calculate its UMPS at 300 Kelvin, it comes out to be close to 422 meter per second. Can you imagine this? This is faster than the speed of sound, which is close to 320, I guess, meter per second. It's faster than that. If I were to convert it into miles per hour, I think it's around 960 miles per hour. And perhaps around 1400 kilometers per hour. Such a huge value. So do not think that these speeds are pretty small. They are very, very huge speeds. But why don't we feel them? Why don't we feel a molecule hitting us with that kind of speed? Because the mass is very, very small. Mass being small, the momentum transfer to us is almost insignificant. If you look at the mass of a nitrogen molecule, that's 28 is the molar mass per mole, gram per mole. And if I divide by the Avogadro's number itself is so big that the mass is non-existent. And when you multiply by this meter per second, it's not going to have any significant impact on you. And even if they did, remember, we are born on this planet. Our blood pressure, everything inside us is based on the pressure that we are experiencing. And this is the pressure, the force with which they are hitting us is what we experience as the pressure. Now, we may not feel it because we are born with it, but if you have a guest from a different planet having a lower atmospheric pressure and coming here, they would definitely feel this particular impact. So, let's get on ahead. Now we're going to look at what happens to the region of low and high speeds. If you look at this graph, it's pretty obvious that the number of molecules having low and high speeds are pretty low in number. And as you can see, the graph is not symmetrical. Can you see that? There is a longer tail here, and therefore this speed is not at the center of this range. The speed is not the center of this. It's not an average speed. The average would perhaps lie somewhere in the middle. It won't be exactly in the middle, because remember, the number of molecules having these speeds are also changing. But obviously it should be on the, more on the right of the UMPS. So this is the fraction of molecules having very low and very high speeds are small in number compared to the molecules with the moderate speeds. If I consider these as high and these as low, they're pretty low compared to the area of the region in between the two. So now let's look at what happens when temperature changes. We've already seen this. When temperature decreases, the graph goes narrower and taller. So this is the temperature T2 and this is the temperature T1, and T2 is greater than T1, and this is UMPS1, this is UMPS2. Obviously higher temperature will have higher MPS, but the lesser the fraction of molecules having that. So on increasing temperature, the UMPS will increase, expected. On increasing temperature, the fraction of molecules having UMPS decreases, because remember, there's a greater spread. And you'll also notice that the ones with the higher speeds are greater than this particular area. This area is greater than this area. So higher speeds are greater for higher temperature. Higher speeds are not that great for lower temperatures. So on increasing temperature, the curve near the OUMPS broadens. This indicates that more fraction have speeds near UMPS. That makes a lot of sense. Can you see it's broader and this is more narrower? Because broader always means you have greater range. And on increasing temperature, more fraction of molecules have higher speeds compared to those with the lower speeds. As you can see, this area is going to be greater than this area. So next we're going to talk about the molar mass. Now, if I were to take two gases with different molecular masses and they were kept at the same temperature, they will have different graphs, obviously. And the graph goes somewhat like this. This is the lower molecular mass and this is the higher molecular mass. So the lower molecular mass has a higher UMPS than the one with the lower one. Because for the same kinetic energy, since they are the same temperature, they will have the same kinetic energy. The one with the greater mass is going to have lesser speed, lesser velocity. So the same temperature, UMPS is greater for the lower molecular weight, for the lighter gas. And effect of M and T are opposite. So let's talk about UMPS now. Let's derive this. And we are going to use the same equation. There's no need for this derivation for you to learn. I'm just showing you so that you can appreciate how we get this. This is the equation we started with, and then it became this. So if I want to go maximum, remember this is the graph, this is Y. Remember this is Y and this is X here. This is X here. So the graph was drawn between Y and X and I got that curve. How do you get a maxima? Because UMPS is at the height, it is at the maxima point. So I do dy by dx, which means I do differentiate this with respect to u and then equate it to 0. So I have a derivative of this, which comes out to be this. I equate it to 0 for getting maxima. and this is what I get in return. And this is what we get. We substitute U as UMPS, and this is what we get: 2RT, under root of 2RT by M, 2P by D. Now let's talk about the average. Now this is where things get pretty interesting now. Now before I do the average value and try to tell you what the average value is, we must understand that, remember we're talking about speeds. So when it comes to speeds, average speed makes sense. But for kinetic energy, we need velocity. We don't need speed, we need velocity. And remember, the average velocity of a gas molecule at any temperature is 0. Now this may come to you as a shock, at least to some of you maybe. Average velocity is 0? Yeah, because velocity moves in all directions. So whatever is the probability of a certain number of gas molecules moving in the positive x, you have similar probability of them moving in the negative x. So if you were to take an average of all the velocity, they will all cancel each other out. The average velocity is 0. Therefore, in kinetic energy, half mv square, we do not use v as v average. Because average velocity is 0. Average speed is not 0. And we are about to derive average speed. But average velocity is 0. So v square, so what do we do for half mv square? What v do we use? Do we use vmp? No. We've already seen that is not the velocity possessed by the majority of molecules. Majority don't have that. Only 2000 molecules had that, remember? The 8000 didn't have that. So what's the point in using something which we almost certainly know that the molecule doesn't have? Though the name may suggest something, most probable speed, but the name has nothing to do with what it actually represents. So what do we use? We use a kind of an average, but we use the average of v square. Rather than taking the v average and squaring it, because v average is 0. So it would make more sense to take the v square before you average it out. And that is what the root mean square speed comes out to be, or root mean square velocity comes out to be. And they are same basically. So in half mv square, v is not v average, v is v RMS, where v RMS is supposed to be an averaged version of v square. And the moment you do v square, all the negative will become positive. So you take all the v squares and then you average it out, and that is much better to use in half mv square than the v average, which is 0. So it is the average speed of all the gas molecules, and this is what it looks like. But remember, not all molecules have different velocities. N1 may possess N1 molecules may possess U1, N2 may possess U2, N3 may possess U3. So instead of adding N1, U1, N1 times, I'll just multiply N1 and U1. Rather than adding U2, N2 times, I'll multiply these two. So this becomes this. And it's still the same, average. So based on this, I would say that the U average is an integral of U dN by N. And where U is the velocity possessed by dN number of molecules. So dN is the small number of molecules which possess a particular speed U. And this is the N, the total number of molecules. So when I substitute this from the equation that we had, I get this, and I'm integrating this from 0 to infinity. I get 8 RT by under root of 8 RT by pi m, or 8 P by D. Alright, so next one, U RMS. As I said, this makes more sense in using in kinetic energy. U RMS is always better because it's the speed as well as the velocity. It is the square root of the mean of the square of the speeds. So it is basically this. And since N1 possesses U1 and N2 possesses U2, it becomes this. So from this definition, if I square both sides, I get U square RMS is integral of U square dN by N. Substituting this from the equation and integrating it, I get under root of 3 RD by M, or under root of 3P by D. So let's look at the ratio of these speeds. And you'll always find the URMS to be higher than the average higher than the MPS, because remember MPS was not in the middle, average would be sort of in the middle, but then it's rather difficult to figure out where the average is because the curve is not symmetrical. but definitely should be in the right of MPS, and RMS seems to be better than that. Even in the graph, you'll be able to understand why RMS is much better to be used than average. Because when you look at this graph, you'll find that this is the UMP, this is the average, and this is the URMS. And as you can see, this graph has a longer tail, which means a lot of molecules have higher velocities. And therefore, URMS is much more closer to the higher velocities than it is to the lower velocities. And average, you can say maybe could be somewhere in the middle of this, though it is rather difficult to figure out where the middle is, but somewhere here, MP is definitely on the left of it because it's not a symmetrical graph. So now let's extend the Maxwell distribution to kinetic energy, which is what they essentially wanted to do. So we know that kinetic energy per mole is half capital M U square. From U from this becomes 2E by M, where E is the energy, the kinetic energy. And if I differentiate this, dE becomes this, and U du becomes this. So remember the equation was like this. If I substitute the value of U from here, plug in this value, U du value you plug in from here, the effective equation becomes somewhat like this. And so similarly, you can bring the N down and the dE down, just like you did in the graph for number of molecules. And if you were to plot the curve between the left and the E being the x-axis and the 1 by N dNE by E on the y-axis. Now what does this represent? This tells you the fraction of molecules having speed, having energies E and E plus dE. So the graph is very similar to the speed graph. And if somebody were to ask you, okay, what does this area mean? It tells you the number of molecules, the fraction of molecules having energy between E1 and E2. So that is what this means. And that is the end of the Maxwell-Boltzmann distribution. I suggest you watch this video as many times as it takes for you to really get it. It will take some time to get it. In fact, making this video itself takes me a lot of time to figure out the best possible way to explain it. I'm doing my best, but I'm sure there will be a lot of instances where I can actually improve on them. And so if you like this video, if this video helped you, please do hit the thumbs up button. Check up the other videos of this channel. You'll find a lot of videos on physical chemistry and organic chemistry. And I'll be very soon I'll start with the inorganic chemistry once the gaseous state is over. And if you find those videos to be useful, do subscribe to this channel and hit the bell notification for intimation of future video uploads. With that, this is Kalyan Kumar signing off. Have a wonderful day. Goodbye. Thank you for watching this and see you all in the next one.